Multi-ton machines hanging motionless in midair. You've seen it so many times you simply accept it as normal. But stop and think about it for a moment. A conventional aircraft, the same weight as a helicopter, would fall from the sky the instant it stopped moving forward. Something fundamentally different is happening inside a helicopter, and we're going to pull that difference apart and examine every piece of it. A helicopter in hover creates its own wind, forcing air downward through the spinning rotor disc to keep itself aloft. Each blade, thin and fast, sweeps out a circle that acts as a self-powered lifting surface. This is not just a wing in motion. It is a machine generating its own pressure difference, building lift from rotation alone. Momentum theory puts a number to this. Induced velocity equals the square root of thrust divided by 2 times air density and disk area. The larger and faster the disk, the less velocity needed to support the aircraft's weight. Rotor tips slice the air at 200 to 240 meters per second, always kept just below the speed of sound to avoid destructive forces. Disk loading, the weight divided by the swept area, shows the trade-off. Light helicopters spread their weight wide, needing less induced velocity. Heavy lifters concentrate force, demanding immense power. Every second in hover is a contest between blade speed, disk size, and gravity, with power requirements rising sharply as demands increase. Igor Sikorsky believed he had solved the puzzle of vertical flight, but the skies had other plans. In 1942, during a test of the R-4, the machine suddenly spun out of control. The rotor did its job, lifting the aircraft, but the fuselage twisted violently in the opposite direction, almost hurling Sikorsky and his crew to disaster. The logs from that day describe a cockpit gripped by centrifugal force, pedals useless, ground spinning into a blur. This was not a minor setback. It was a blunt lesson from physics. Every action has an equal and opposite reaction. The main rotor's force was answered by a matching torque on the fuselage, and without a way to counter it, the helicopter became a lethal carousel. Early accident reports from the Smithsonian archives are filled with similar stories. Uncommanded spins, ground loops, shattered tail booms. Each crash forced designers back to the drawing board. Sikorsky's near miss made the need for an anti-torque device undeniable. Out of risk and failure came the tail rotor, a small but essential innovation that would give pilots the authority to hold a heading and keep the machine stable in hover. The price of progress was paid in bent metal, bruised egos, and hard-won understanding. Every second a helicopter hovers, the pilot's feet are locked in a contest with physics. The main rotor's power tries to twist the fuselage into a spin, so the pilot presses the pedals, adjusting the tail rotor's pitch to push back with just enough sideways thrust. This is not a set-and-forget mechanism. The tail rotor must match the main rotor's torque, moment to moment, and that balance is never still. Pedal movement travels through a mixing gearbox, translating a few centimeters of foot pressure into a precise change in blade pitch at the tail. Even in a stable hover, the pilot's feet are alive with corrections, fighting drift and gusts, chasing the invisible line between control and chaos. The numbers are humbling. The tail rotor delivers only about 5 to 7% of the total lift, yet that sliver of thrust is the difference between holding a heading and spinning out of control. A single misjudged pedal input can send the nose slewing or the whole machine pirouetting. The pilot's calves ache from the constant tension. Unlike the collective or cyclic, which move for climbs or turns, the pedals never rest. They are the live wire of anti-torque, the pilot's only defense against the main rotor's relentless demand for symmetry. In the cockpit, this footwork is not finesse. It is survival, and it never ends. Commands from the cockpit pass through a single spinning hub, the swash plate. Hidden beneath the rotor, it translates every pilot input into precise blade movement. Raise the collective lever, and the stationary plate lifts, increasing all blade angles together. In most light helicopters, blade pitch shifts from 0 to 14 degrees. That narrow range separates a gentle descent from a vertical climb. The collective's linkage ratio, about 1 to 3.5, means each inch of lever travel nudges the swash plate less than 1/3 of an inch, delivering a pitch change of roughly 0.2 degrees per degree of lever movement. The cyclic stick adds complexity, tilting the swash plate so each blade's pitch rises and falls in a wave as it spins. With a linkage ratio near 1 to 2.8, the cyclic must overcome the rotor's centrifugal force while allowing for subtle corrections. This creates a blade pitch envelope that is both tightly constrained and endlessly responsive, mapping the pilot's hand to the sky. In hover, the swash plate never rests. Collective and cyclic inputs merge, sending each blade through its own pitch path every rotation. Even a worn bearing or 1/10 of a millimeter of extra play can turn precision into risk. Pilots say the stick is always alive, demanding constant attention. Hovering, the machine is balanced on a knife edge. Each moment is a controlled emergency, every blade a direct translation of human intent. A helicopter can betray its pilot in seconds if the invisible rules of airflow are crossed. Sink too fast, over 500 feet per minute, while holding a hover, and the machine can slip into vortex ring state. The blades, instead of slicing clean air, start recycling their own downwash, trapping the aircraft inside a toroidal vortex. Suddenly, lift vanishes. The controls, once crisp and responsive, turn soft and vague. The cyclic feels mushy, the collective heavy and ineffective. No amount of added power helps. In fact, pulling more only feeds the vortex, deepening the descent. Training manuals set a ceiling of 300 feet per minute for hover descents, a hard limit hammered in by accident investigations and cockpit voice recorders filled with confusion and alarm. Instructors drill the recovery, push the cyclic forward, break out of the column of disturbed air, and regain translational lift. Sometimes, a sharp sidestep with lateral cyclic works even faster. The only way out is to escape the vortex grip, not to overpower it. Every pilot learns to respect this regime because once the vortex ring state takes hold, the margin for error shrinks to a handful of seconds and a few dozen feet. The lesson is clear. In vertical flight, more power can mean less lift, and the only true safety is knowing how to fly out of your own wake. Engine failure in a helicopter is not a death sentence. The moment the engine quits, a freewheeling clutch silently disengages, letting the main rotor spin untethered, driven now by air rushing up through the blades as the aircraft descends. This is autorotation, a physics trick every pilot trains for. The collective lever drops to minimum, flattening blade pitch and keeping rotor speed alive in the safe band, typically between 300 and 400 revolutions per minute. In a Robinson R-22, that means holding the needle above 300 revolutions per minute, eyes flicking between the tachometer and the horizon. The descent is steep but controlled, a glide ratio of about 1.5 to 1. As the ground approaches, the pilot pulls the collective sharply, a maneuver called the flare, converting stored rotor energy into a burst of lift that slows the vertical drop. Done right, the touchdown is gentle, proof that even without power, the machine can save itself. This is not luck. It's the physics of airflow, clutch, and blade inertia, drilled into muscle memory. At the summit of Everest, the rules of flight are rewritten. Here, air density drops to barely a quarter of what blades enjoy at sea level. Each revolution of the rotor has to do the work of 4, just to keep the machine from falling. On May 14, 2005, Herbert Kessler gripped the collective of his AS-350B3, holding it steady at 70%. Any less, and the rotor would slip below 300 revolutions per minute, the critical threshold where lift collapses. The engine strained, robbed of power by the thin, oxygen-starved air. Modifications mattered. A high-compression turbine, extended blades, every ounce of weight stripped away. Kessler later wrote that the margin was razor-thin. The collective had to stay high, or the summit would win. At this altitude, hovering is not just difficult. It is an act of defiance against physics, revealing the true edge of what thin blades can achieve. Engineers have never stopped searching for better ways to tame the forces unleashed by spinning rotors. The NOTAR system, for example, replaces the tail rotor's exposed blades with a high-pressure fan buried inside the tail boom. Air is forced through slots along the boom, using the Coanda effect to create a sideways jet that counters torque. This approach trims noise by up to 6 decibels and eliminates the risk of tail rotor strikes, but it comes at a cost, an extra 35 kilograms of fan, ducting, and heat shielding. Maintenance shifts from blade tracking to fan bearings and duct inspections. Coaxial contra-rotating rotors, as seen on Kamov helicopters, solve torque at the source by stacking 2 main rotors spinning in opposite directions. The payoff is a compact footprint and high hover efficiency, but the gearboxes are a marvel of complexity: concentric shafts, planetary gears, and dual clutches, all packed into a structure that is both heavy and expensive to maintain. Each innovation rewrites the trade-offs. NOTAR trades simplicity for silence and safety, and coaxial designs trade mechanical elegance for brute force performance. The evolution of anti-torque is a lesson in engineering priorities. Sometimes the solution is not to perfect what exists, but to invent a new way of solving the problem altogether. Every stable hover is a delicate negotiation with chaos, a controlled emergency renewed every second. Today's helicopters transform raw physics into an improbable balance, not despite their thin blades, but because of them. What looks fragile is, in truth, an engineered defiance of gravity. That paradox still hangs in the air.